yeah, quantitative questions for Lagrangian submanifolds. So I'm just going to work in R4 with the standard symplectic form. So it's right. So we just use x and y coordinates. Right, so dx. Bless you. Or sometimes you identify it with C2 as well. So it's C2, and then we can and then use complex coordinates. All right. So I'm interested in Lagrangian submanifolds. So all right, so since it's in R4, this is going to mean Lagrangian tori, and these things definitely exist. Right, so Lagrangian tori, like for example the product tori. So we'll denote LAB using the complex coordinates. This is pi c1 squared, pi c2 squared. All right. Okay, so I'm interested. So what do Lagrangian submanifolds look like? What can you do with them under Hamiltonian diffeomorphisms? And two natural questions are packing and squeezing. All right, so let's remind you what those are. All right, so the packing question. So you need a target. All right, so if we're given maybe an open set in R4, maybe if we could fix A and B as well, then does there exist a Hamiltonian diffeomorphism? All right. Sorry, this is not the pack. This is the squeezing. I guess I'm calling this squeezing, by the way. Squeezing. If there's just one, squeezing. Right. Okay. So that's all right. So it's right. So in other words, right. So if U is fairly small, can you somehow wind up the Lagrangian and put it inside? Packing. Right. And then you can also ask about packing. Right, so packing question. Right, so packing means instead of getting one Lagrangian inside U, I want to get more than one. All right, so you could say, so does there exist? So with the same U, maybe the same A and B. Right, so does there exist maybe n of them? Right, so phi 1, phi n, such that right. So phi k. Right, whatever the Lagrangian is. So right, so the image of the Lagrangian is contained in U, and phi k. Right, so they're disjoint. All right, so that's okay. All right, so that's packing and squeezing. So there's variations on these questions. If you're given U, you could ask for kind of restrictions on Maslov class, area class of embedded Lagrangians. You could put different hypotheses on the images. Maybe you want them all to be Hamiltonian isotopic or not. But that's it. All right, so I'm going to try to answer these. Right. So okay, so what's novel? Right, so it's so where these things have been well studied is if you, instead of a Lagrangian, you have another open set instead. Right? So the other case is if you replace a Lagrangian submanifold by an open set V. All right, so, but then the difference is in this case there are volume obstructions. All right, so then you could say so then you can ask if volume is the only obstruction. Right, so I'm talking about Hamiltonian diffeomorphisms. Volume is the first invariant. And if you're trying to embed one open set in another open set, the volume has to be monotonic, I guess. Right, but in my case, since I'm working with submanifolds, there's no volume obstruction. Right, so So it's right. So somehow, so now there's not obviously any obstructions at all to doing this in any scenario, right? Okay, so you can try and do that. So there's no volume, there's no classical obstructions. So then if we're talking about Lagrangians, the other thing is flow homology, and it's not obvious that that has anything to say about it either. So another thing you could ask, well, you could try to apply flow homology. But again, it's just somehow non-trivial, right? Because I'm working in R4, so any flow homology is 0, so it's not clear you can get anything out of that. And we tried, but okay. So anyway, so I'm trying to answer these. Right, so it's okay. All right. So we know. It turns out. So we know some answers to the squeezing question, and some open questions, I guess, about the packing question. Okay. So as far as squeezing goes, right. So squeezing, there's some answers, at least for simple U. All right. So it's right. So let's suppose. Right. So it turns out toric domains are the easiest to work with. So I want this domains defined in terms of absolute Z1 and absolute Z2. So for example, U could be a ball. Right, so write this as a ball. There's a C here. All right, so this is the sum. Right, so you call this a ball of capacity C. So its radius something like square root of C over pi. So suppose U is a ball, or polydiscs are the other things. So you can also look at a polydisc. It's a set of pi. That's there. Right, so these are both toric domains. Right, so take U to be one of those, then I'll tell you the answer to the squeezing question. Okay. Right, so the notation's set up to make the results look nicer. So theorem, it's with Opstein. Right, okay, right, so L. All right, so you take one of these product Lagrangians. It's actually still, more or less, it's still an open question whether this is a full list of all non-monotone Lagrangians in R4, conceivably Hamiltonian isotopic to one of these. So restricting to these might not be a big assumption here. Anyway, all right, so L1x. And also it's enough to look at product Lagrangians in this form. All right, so by reversing the factors, we can always assume, all right, so it's, we'll take x to be bigger than 1 as well. So it's enough to look at product Lagrangians of this form, because you can always reverse the factors, make the first factor the smallest, and then rescale to make the first factor 1. So look at this. Okay, so this maps into a ball, right? So this means, for right now, or like this means by a Hamiltonian diffeomorphism. Right? So by a global Hamiltonian diffeomorphism. Of course, you can always get a symplectic embedding from a neighborhood of this to like an epsilon-sized ball. Right? So all Lagrangians have standard tubular neighborhoods. So for this kind of question to make sense, we have to be talking about under global Hamiltonian motions.
Can you repeat that?
Well, or you could say by global symplectomorphism would be fine. But I'm saying you can't take a local.
Yeah, can you repeat why? Like, what's the global symplectomorphism?
So if you take any ball you want, there's always a Lagrangian torus in there, just like an epsilon circle by an epsilon circle, and a neighborhood of that is symplectomorphic to a neighborhood of this, just by Weinstein's theorem. That's nice. Yeah. But yes, I'm just kind of emphasizing because you don't have to care about that if you're dealing with open sets, but in this case, it really has to be a global thing to make sense. Okay, so this is here. Right, then this is if and only if. So C has to be, so it's greater or equal to, greater than actually. Right, so this ball's open. Let's be careful. Right? It's an open ball. So this is true if and only if C is strictly bigger than the maximum of 1 plus x and 3. Right. So in other words, right. So x goes along here. Right. So so somehow the optimal embeddings it's linear between 1 and 2, and then it's just constant the rest of the way. That's it. Right, so that tells you exactly when there's a global Hamiltonian motion which puts a Lagrangian torus inside a ball. Right, so sorry about that. Right, so some remarks about this. It's always right. So since everything is toric here, it's interesting just to project onto the absolute Z1, absolute Z2. So right, so we have this moment map Z1, Z2. Apply Z1 squared. And you can just describe domains by their image. Right? So if you're looking at a ball, right? So a ball comes down as a right-angled triangle, isosceles triangle. Right. Okay. So if we take L1x, right? So L1x, that's its image here, and this diagonal line, that's the boundary of a ball of capacity 1 plus x. Right? So the Lagrangian naturally is sitting inside the boundary of this ball. Right? So what I'm saying is, if x is less than 2, so I'm talking about this by, suppose, the Arnold's conjecture or some kind of thing. It's impossible by a locally supported Hamiltonian to push this thing inside. So you can't kill all intersections between the Lagrangian and a push-off of itself by a Hamiltonian with support near that Lagrangian. Right? So it's impossible just to nudge the thing inside the ball. Right? This theorem saying if x happens to be less than 2, you can't do a global thing to move it inside the ball either. Right? But if x is bigger than 2, then there is a Hamiltonian which kind of moves it outside in R4 and puts it inside a strictly smaller ball. Right? So what I'm saying is, so in other words, right, so you can push L1x strictly inside. Right, so only if, I suppose if and only if x is bigger than 2. That's somehow what it's saying. Right. So, right, so if x is less than 2, the inclusion is as tight as you can squeeze it. Right. So that's somehow what that's saying. The other thing, I've got a few things about this. The other thing, so Lagrangian submanifolds up to Hamiltonian diffeomorphism. There's natural invariance, right? The Maslov class and the area class. But somehow they're not enough to answer this question either, right? So another thing, if we take Lagrangians, things like, I remember this right, so things like 1, 2, 2, 3, it turns out there's not a Hamiltonian diffeomorphism which takes one onto the other, but it's somehow not obvious. Right? So we can look at sort of a basis for the homology. Right? So we have that's right. So these have bases. So these are integral bases of the first homology group just in terms of a standard basis, one factor, the other factor. So you could take sort of E1, E2 here. Right? So this is the standard basis of the homology. Here you could do something like 2E1 minus E2, E1. So these are both integral bases of homology. All right? But all these classes have Maslov index 2. So they're Maslov 2 bases. E1 has area 1, 2E1 minus E2 has area. Right? So the areas, right? So E1 is 1, E2 is 2. 2E1 minus E2 is 1. And E1 is 2. So somehow by Maslov class and area class, you can't distinguish these two. And in fact, since so L1, so by this thing, right, so L1, 2 sits inside B3. That's optimal. Right, because x is less than 2, less than or equal to 2. So I can't squeeze this inside. But if you go here, L2, 3, well, it's basically a rescaling of 1, 1.5. 1, 1.5. Again, the inclusion is optimal. That sits inside 2.5. So then if you scale it, this goes inside B5 optimal. I mean, so there's other proofs of this, but anyway, these Lagrangians are different in terms of squeezing, even though they have the same Maslov class and area class. Anyway, so that's true anyway. Know a lot about this actually. Now we're on. Right, so, well.
What are some other arguments for why they're different? You said there's.
You can use displacement energy. Is probably easier. Right? So this has displacement energy 1. This has displacement energy 2. So I think for that you have to go back to kind of Chekhanov's argument. Right? So if you displace, you get a Maslov-2 disk bubbling off. So here you can imagine, this has displacement energy 1, you can imagine a Maslov-2 disk of area 1 bubbles off. And here, if you choose the right complex structure, the smallest area of a Maslov-2 disk is 2. So, okay, counting areas of Maslov-2 disks, I guess. That's fair enough.
I'm sorry, this is probably not important, but are these closed balls?
Open. Yeah, this is true. I want them to be open because otherwise this is not true. So I think we'd have to put maybe a bar on the top of this. Anyway, if you know, okay. Right. Well, okay, right. So by the way, right. So L. All right. What can I say here? If the Lagrangian goes inside a ball, of course, this doesn't imply. So also, this thing sits inside the boundary of a polydisk, right? If you go P1x. Right. So Lagrangian embeddings don't necessarily extend to the polydisk. Right? So instead of a polydisk. All right, so polydisk, this thing. So this is just the moment projection is just a rectangle, and then the Lagrangian sits on the corner of the rectangle. So if you can embed the Lagrangian, it doesn't necessarily imply that you can embed the polydisk. Because the polydisk is an open set, so it needs volume to embed it. So certainly, right, so you can... right, so it's right. So Lagrangian embeddings don't necessarily extend over the whole polydisk, but it turns out it's maybe this is sorry, this is being proved. But, right, so there's a guy. What's it called? Right, so Kyla Siegel, I think, proved something about this. There's a grad student also at Michigan, Daniel Irvine. So it turns out this Lagrangian embedding question is related to the stabilized embedding question for polydisks, right? So the theorem is, right, so P1x, if you add some factors, right, so maybe some CK here, this goes into BC. So actually, maybe this is me, actually. I think I proved some of this. Right, so, okay, anyway, right, so BC, CK. Right, and then the answer is the same. Right, this is, so if and only if. All right, so it's so somehow it's kind of interesting. So it's right. So Lagrangian embeddings aren't a full list of obstructions for the polydisk, but somehow if you stabilize the question, they seem to capture everything in that case. I don't okay, I sort of know. It's not completely obvious why that's true, though.
Is there any way to think about starting with the Lagrangian embedding and trying to extend it over the polydisk and hitting some kind of obstruction?
Right.
There's some way to rephrase what
Yeah.
I mean, you're saying
Right.
C volume, but
What do I see? No, there's no volume. This stabilized question has no.
I'm saying
In dimension 4.
In the 4-dimensional case, you have the Lagrangian embeddings that you can't extend to the whole polydisk. And your argument was because the polydisk has volume. Start with the Lagrangian embedding and try to extend it
To a stabilized polydisk embedding, though.
Well, I was to some subset of the polydisk.
Oh.
C,
Yeah, right. I don't know. I mean, right. I mean, the only thing I was thinking is if you take a Lagrangian, or really the moment projection of it, right? And this is the moment projection of the polydisk. But you could try and embed sort of all fibers of this. I mean, typically if you did that fiber by fiber, they'd start overlapping. But if you have the extra dimension, you can try and sort of push some of them up in the extra dimension and sort of get a stabilized embedding of the polydisk. So I think that's sort of why I think this should be kind of intuitively true, but it's a bit. But in dimension 4, there's going to be a whole mess, right? I mean, there's no,
Right.
Let's think about this. Okay. Oh well. Okay. Right. So by the way, right, so this is kind of surprisingly simple, right? So the famous paper of McDuff and Schlenk, right? So the McDuff right, so, well, what it is. I'm going to say what it is. Anyway, they computed this function, right? So it's a Duff-Schlenk function, which is sort of the infimum of C, such that I haven't told you what an ellipsoid is. I'll tell you in a second. Right. So an so we need it in a second anyway. Right. So an ellipsoid goes into a ball. Right. So an ellipsoid is a generalization of a ball, I guess. Right. So it's something like this here. So 1x. Okay. Right. It's toric. This is P of the ellipsoid. So they worked out this, and it's an infinite. At least the first part of it is an infinite step function. So it's very complicated. So there's an infinite. So this is an infinite step function. Part of it determined by the Fibonacci numbers. Right. So these questions can be very awkward in dimension 4, but somehow, if you're just interested in Lagrangians, it's fine. All right. Does this help? I don't know the answer to the packing question. I don't know.
I mean, you can take like volume arguments, right? Like if you're an embedding, then you extend it to some stabilized.
Oh, think about this stabilized question. Yeah. Both sides have infinite volume. Yeah. So somehow it's really no volume. I mean, which is kind of why it's related to Lagrangians, maybe. Well, I'll talk about the packing question a little bit. I'm not sure if it has anything to do with anything, but maybe. All right. Oh, well, anyway, what you can do, there's a similar question for, a similar answer for polydisks. Well, by the way, right, this question. This one is open, by the way, as well. At least for x bigger than 2.2 something. So it's unknown, actually, when a polydisk embeds in a ball. So we know the stabilized case, but we don't know the basic one. But Lagrangians I know, right? So part of this optioning. Right, so L1x P B. Right, so I want to assume we ordered the factors there as well. Right, so it's if and only if. Let's be careful here, right? So either A is bigger than 2, or A is bigger than 1, and B is bigger than x. Strictly bigger. So good, right? So it's a similar kind of thing. So as long as the smallest factor gets bigger than 2, that's it. All obstructions vanish. So in other words, all of these things you can put inside a cube whose capacity is 2 and a bit. Right. Okay. So anyway, so that's squeezing. So there are some sort of symplectic obstructions left over, but not too many, and more than displacement energy somehow as well. All right. Okay. So then, makes sense. Right. So then, okay. So then packing. Well, I was just going to skip everything else about this. Any questions here? All right. So anyway, so packing. All right. So this seems okay. Right. There's different variations of this question. So we're going to phrase it in kind of a nice way. So the question I want to ask is, so we're given the domain. All right. So if we're given usually a toric U. Right, so I want to somehow, right, so how many, all right. So instead of assuming that all the Lagrangians are Hamiltonian isotopic to a fixed one, I just want to assume that they're integral. Right, so let's see what that means. So how many integral Lagrangian tori disjoint, okay, or disjoint, or can be disjointly embedded in U. All right. So integral just means that if you integrate omega, that gives you a function from, okay, right, so sort of relative pi 2, I guess. And this takes integer values. Right? So in other words, any disk with boundary on the Lagrangian has integer area. Right. So you could, there's other questions you could ask. Well, like I was saying it before, you could assume that I'm just looking at embeddings of a fixed Lagrangian. Right? So this is somehow more general. And maybe a more interesting thing, you could ask for all the Lagrangian tori to be Hamiltonian isotopic inside U. And then maybe you've got a better chance of doing flow homology. Or at least proving the answer is 1, maybe in certain cases. Anyway, but the benefit of this question is that there's a nice sort of guess of an answer. This is supposed to be a packing question.
Actually, can I ask a question about the embedding part?
Oh.
You know, so to prove your theorems, you need obstructions and constructions. And your obstructions, do they not really come from floor homology? They come more like from...
For this, or for embeddings?
For embeddings.
No, they come from...
They come from stretching.
Right, exactly. Right, they come from stretching.
Kind of like
Right.
sand.
Yeah, kind of right. So, so if you have like, okay, not really a toric picture, but anyway, you have a ball, you have some kind of Lagrangian torus in there, and then you have this Weinstein neighborhood, which we understand pretty well. All right, so like a neighborhood of the zero section in a cotangent bundle, and then you put a little thin ellipsoid in there, which we know all about. So, well, me and Dan. So studying ellipsoids inside balls, we're kind of expert on these by now. So you can find like a holomorphic curve of high degree inside the ball. It's supposed to be some high degree holomorphic curve, and then it winds around the ellipsoid a large number of times. Then you study a holomorphic curve like that, and then you stretch along the boundary of the Lagrangian torus. And then, right, so then these curves degenerate, and it turns out they degenerate to kind of disks outside, or planes outside the tubular neighborhood of the Lagrangian, isotopic to asymptotic to geodesics on the Lagrangian. And then you kind of count areas, and 3 pops out of this. So it's right. So anyway, so that's
the curves themselves that you're stretching are more like in your paper with Ali.
right. Yeah.
And then
Yeah.
the constructions are like folding kind of.
Right, kind of, yeah, sort of, right, kind of. I mean, at least they're definitely elementary things. So it's kind of like winding the Lagrangian round itself, but you're using that it's Lagrangian, right? So you can kind of like keep winding a huge number of times, and you don't create intersections. Man, it's one of those things that everything just seems to check out. Yeah, okay, anyway, but, well, we can come, okay, I don't know if we'll come back to that. But, right.
So you use your knowledge of ellipsoids in balls just to guarantee the existence of some curve?
Right, yeah. So it's like all these embedding questions. At any time you want to obstruct an embedding, you kind of you sort of think of a cobordism. All right, so like if I'm embedding V in U, you kind of look at some cobordism from the boundary of U to the boundary of V, and you want to prove that there exist holomorphic curves in there. And then the argument is once you know these curves exist, they're holomorphic curves, they have to have positive area, therefore that gives you some kind of obstruction. So the question is how to show that curves exist. Well, and the argument here is that I know that curves exist between balls and ellipsoids. So in my case, right, I have the boundary of the ball here. You have the boundary of the kind of epsilon neighborhood of the Lagrangian. Right? And then we have some kind of ellipsoid down here. Right? So I know that there's curves between the boundary of the ball and the ellipsoid, and then you sort of stretch along here, and then what's supposed to pop off is planes out here. And if these are going to have positive area, that implies this obstruction.
So the fact that the Lagrangian is a torus plays no role?
Oh no, it plays a big role. Okay, like because to do this stretching, I need to know exactly what the Reeb dynamics are on the boundary of the tubular neighborhood. Yeah, so if it was a different Lagrangian, it'd be completely different. Right. Yeah, right. So I need to know exactly what the geodesics are, what the Maslov index is, this kind of thing. Right. Yeah. Right. Yeah. Okay, right. Oh, well, so anyway, right. So why am I interested in integral ones? That's because you can draw nice pictures, right? So in this case, an integral. Right. So now, okay, it's in this integral case, right? So now there exists natural, easy to draw packings. All right. So you just take your toric domain, right? So you take U to be something toric, and then you project it. You get some kind of set, right? This is what's going on here, right? So pi z1 squared, and then you just take all integer points inside here. How many are here? So you take all integer points. Now there exists natural packing. So in other words, the natural packing is just the union over all pairs KL, such that. Anyway, right. So such that KL lies in the projection of the domain, and then you go like this. Right. Okay. So in other words, the pre-image of these dots give you a packing of the of U, and then you can say is that, and that's a natural packing by Lagrangian tori, and they're all integral. Okay. Right. Z squared here. They're all integral because K and L are integers. So that's it. Okay, and then you can say, right, so this is kind of all you can sort of see, and then the question is that maximal? So apparently I think this is due to Carchon. Right, so is the packing, right, there's natural packing here, right, so is the packing maximal? It's a little bit different to the question we had before, right? So I'm not saying how many you can pack. I mean, it's a slightly simpler question. I'm just saying, is this a maximal packing? So in other words, is there an integral Lagrangian tori which misses all these, which is disjoint from these tori? Well, so that. Well, so this turns out to be a little bit tricky here. Right. So okay. So it's just two. Well, the easiest case here is if we make U to be a cube. All right. So this is so one thing. So this is with Kerman. Right. This is right. Okay. So what we say, right? So if C is less than or equal to 2. Then, right, so then you can look at just the 1, 1 Lagrangian that's sitting inside PCC. So, right, so PCC is just the square. Well, I guess I'm assuming C is bigger than 1, I guess maybe here. Then there's, right, then you can take L11 inside there. And then I claim, yes, that is maximal. And that is maximal. Well, so maybe we'll come back to this. So this is a little bit, subtle. So what am I saying here? So I'm saying, in other words, well, okay. Well, yeah. So remember, P. I'm assuming this is open. So even if you put C equals 2, you can't stick that. Okay. Right. So well. Okay. So another way. Right. So well. So just about this. Right. So it's so actually the previous results, more or less. Just right. So prior. So the previous results. Well, it's not quite what we need here, but if you took say L12, it doesn't embed in this because both factors are strictly less than 2. So L12 doesn't embed. I mean, and then sort of the same kind of analysis says, if there is a Lagrangian torus in here, it has to be monotone. If there is an integral Lagrangian torus, it has to be monotone. So in fact, any integral Lagrangian torus in such PCCs are monotone. In particular, there's no Hamiltonian embedding that takes L12 inside this thing. So this is purely about monotone Lagrangian tori. right? Then what this is saying is, so it's saying, so in other words, the theorem says any monotone L intersects this Clifford torus here. All right, so we'll talk about this at the end if there's time for this. Right, but this is not totally clear here, right? So the catch here is, well, first of all, any monotone. This is false, by the way. So it's not quite. That's false. Not sure. Right. Okay. I'll take that back a second. Well, I'm only claiming this for tori. I'm not claiming it for any. Maybe I know it for any, but anyway, right, so just right. So what the theorem is saying is any monotone Lagrangian torus has to intersect L11. Right, but the catch is, according to Vienna, maybe 5 years ago, right, so 2016 maybe. Right, so there exists infinitely many monotone L in PCC, well, let's say in P22, none of which are Hamiltonian isotopic. Right. So the thing is here, if there was some Lagrangian in there which was right, if there was some Lagrangian in here which is Hamiltonian isotopic to L11, well, actually none of them Hamiltonian isotopic to L11. If the Lagrangian was Hamiltonian isotopic to L11, then it would be a result in flow homology. The flow homology would say they have to intersect. But according to Vienna, you can embed a lot of Lagrangians in here, which are just not Hamiltonian isotopic. In P22, right. Presumably they're all Hamiltonian isotopic if you can drift outside, but then flow homology doesn't work. So it's, right. Yeah, right. So I'd want to use flow homology. Oh, bless you. I'd want to use flow homology and kind of compactify it to a CP1 times CP1, and then everything's monotone, and then use this machinery. But because of this, somehow the flow homology might be 0 between the two Lagrangians. So it's something about intersections of monotone Lagrangians, and then sort of an easier fact is it's not true, right? So not all in the same manifolds, right? So not all monotone Lagrangian submanifolds. Let's compactify here. S2 times S2, area class maybe 2, 2, intersect. So you can take the Chekhanov torus embeds in here, and you can make that disjoint from the anti-diagonal. So it's not true that monotone Lagrangian submanifolds intersect, but I'm saying any monotone Lagrangian torus intersects this guy. So that's what's going on here. Anyway, all right. So that's a little bit of holomorphic curves for that as well. But, anyway, right. So the answer to this question then is yes, if U is small enough. But then if U gets bigger, not anymore. Right, so it's right. Okay, so the other half of this, if C is bigger than 2, then there exists. So there's going to be a monotone Lagrangian torus contained in P22, but then it misses. All right, so now, all right. Okay, so C is bigger than 2 actually. So we've got C. So it's 2. Right, so that's my domain. But now there's 4 toric integral Lagrangians in there. Right. So it misses all 4. All right, so it's union K L 1 2 L K L. All right. So in other words, the answer to that question is no. So the natural packings aren't maximal packings. All right. And in fact, L is Hamiltonian isotopic to just the standard product, just the standard Clifford torus. So in other words, and in fact the Hamiltonian you can take to have compact support inside the PCC. So in other words, so what I'm saying is you can start with the L11 here, apply a Hamiltonian motion, and displace it not just from L11 but from the other three guys as well. Right. So it is displaceable because C is bigger than 2.
It exits in that motion.
No, it doesn't.
It stays inside.
It stays inside. Right. Yeah. Right. Okay. So now, right. So I'm not quickly. So there's a lot of tricks. There's a lot of other things you can answer with the same kind of construction. So maybe I'll just quickly show you why this is true. Right. So another right. So just sort of a quick, well, like why is. I mean, you can more or less write the thing down, but anyway. So in fact, you can do a little bit more. Right. So the general. Right. So the proof is so in fact, or a bit more. Right. So there exists. Okay, so again, it's right. So there exists an embedding of. You can take the polydisk 1,1, the closed polydisk 1,1, and you can embed this inside PCC, minus the union of those L's. Right. So, in particular, so not only can you embed the singular part of the boundary of this, you can actually embed the whole polydisk that's inside there. Right. So this thing. Right, so somehow so it's clear you can embed the open polydisk, right? The open polydisk sits inside there by inclusion. I'm saying you can actually embed the closed polydisk, and that's kind of the question. Right. Okay. So I want to talk about why that is true. Right. And then you can see exactly why I need C to be bigger than 2 to get this thing to work.
Can I ask you a question about your previous theorem? Well, I could also save it for the end.
Up to you.
Well, I mean, so Karshan's original question was about open sets, right? Whereas you've been talking about polydisks. Like
No. This is open.
No. But I'm saying an arbitrary open set. Like
Oh, an arbiter. Okay. Well.
Let's say we just wanted to consider an arbitrary open set whose moment projection just contained the lattice point 1, 1.
You want it to be toric, otherwise all this whole thing's obviously false, right? So it wants to be an arbitrary toric.
Sure.
Right.
So how about a toric open set containing 1, 1?
Mm-hmm.
Can your methods still be used to show that natural packing is maximal, or does it?
Oh, it depends on the open set a little bit, right? So it's not true for all open sets.
It's not true for all open sets. That the natural packing containing.
Well, I mean, it's false.
But if it just
If it just contains L11.
If it just contains L11, you know.
Well, no, okay. Right? So you can get counterexamples with this, right? So just look at whatever this P11 looks like, project it down. Okay. I don't know what the projection's going to look like, but it's going to miss these 3 dots. So you could just kind of do something stupid and just kind of take it. Yeah, right. I mean, right. But you're right. I don't know the answer for many. I mean, maybe balls we have a partial answer, but I don't know the answer for many domains. I think it's
Right.
maybe if you assume it has to be convex or something, you might be okay if there's some kind of.
Yeah, sure, right. But it's right. Okay, no, that.
Okay. Anyway, all right. So I want to put this inside here. And so it's right. So trick about this, right? So we want to use polar coordinates, like calc. So it's anyway, right? So I want to use polar coordinates, right? So kind of the symplectic, our symplectic polar coordinates. So RK is going to be the area of the kth factor, and then theta k is the angle. So it's R mod z. Right. So this goes between 0 and 1. Okay, and then we start with a model, right? So start with a model of this, right? So start with P. So something that's obviously symplectomorphic to this, right? So I'm writing it S times T. So S is in the R factor and T is in the torus. All right, so S is going to be something like, maybe I'll just draw it. Yeah. Anyway, this is in the R1, R2 plane, and this is a subset of the theta planes. Right. Okay, what's in here? Right. could have had these right from the start anyway. Right, so R1, R2. Right, so the thing is, I'm allowed a little bit more space than 2. That's the thing here. So you go 2 and a little bit. Right. Okay, so I want to go a little bit less than 2 in one coordinate and a little bit more than 2 in the other coordinate. Right, so this is the S. And then go. Theta 1's are periodic, right? Right, but because I'm going a little bit less than 2 in this direction, I have to go a little bit more than a half and vertical, and then I can go a little bit less than a half. That's it. All right, so, right, and then let's push. Make sure this thing's a nice product. Let's push this thing off the axes a little bit by delta. Okay. So this is a model. This is just a product set. So it's a model for a product. It's just a product of 2 disks. But the 2 disks have area 1 as long as the length of this times the vertical length here is 1. Right. So that's a polydisk, right? It sits where it's supposed to sit. But right, remember there's 4 Lagrangians in here, right? So 2, right? So 1, 2, 2, 2. Actually, it's bigger than 2, right? So here, yeah. Right. So it intersects 2 of the Lagrangians. That's it. Right. Okay. So the goal, well, so that's the first guess, and then the game is to kind of push this P, or equivalently push these 2 Lagrangians off the set. Then I'm done. All right, so the goal, so the goal is to push L11 and L21 off P. This is equivalent to moving P off the Lagrangians. Right. And I want to do this. Okay, so mainly, so mainly using Hamiltonians that depend only on the theta coordinates. There's some cutting off involved in it, right? But mainly using Hamiltonians which depend on theta. So the thing is, if the Hamiltonians depend on theta, then the thetas are invariants of the motion. So when I'm trying to keep track of what's going on, you really only have to worry about points that start in this part of the Lagrangian. All right? Because since the thetas are invariant and the polydisk only has these theta coordinates, you only have to really worry about the parts of the Lagrangians that sit inside this set. Okay, and then how all these things work. The point about this is, since I can push a little bit further horizontally than I go a little bit low vertically, we can assume, one is here, you can assume that this anti-diagonal misses the torus. So that's kind of the whole point of this. Right? So there's a lot of similar constructions, and they're all going to work if you're dealing with a set that kind of misses this anti-diagonal. So that's the thing. So because I've got more than 2, I can move. Well, whichever way we do it. So I can push out a little bit one way, push in a little bit the other way, but I have enough flexibility so that this thing is. Say if you could only take a half, then you would hit the diagonal. As it is, I have enough flexibility to keep the T one side of the diagonal. And the point about this is, because you can do this diagonal, I can look at Hamiltonians that depend on theta 1 plus theta 2 and have fixed derivative on T. So that's going to be kind of the punchline. But anyway, if you didn't know that, right? So let's call this number T here, right? So T is the height on the vertical. So for instance, what you could try to do, you could try to define some Hamiltonian which depends on theta 2, which is say. Okay, so we have to work out Hamiltonian flows. Right, since the thing depends on theta 2, let's say that the Hamiltonian flow is dh d theta 2 times, that's going to be d by dr2. Right. So that's going to be my convention for sign. Right? So if the Hamiltonian depends on theta 2, the flow is going to be in the r2 direction. So you might want to try something that's -1 on 0 to t, okay, up to deltas. So it's increasing, or it's decreasing from 0 to t, and then just because it has to get back down to 0, it's going to have to be rise over run, which is something like t divided by 1 minus t on t to 1. Well, at least that's a continuous function, and then you kind of smooth the thing off. But the problem is, t is a little bit, the good thing about this is, part of this Lagrangian is going to move down. In fact, the part that I care about, and it's going to move down far enough to displace it from the polydisk. So that's fine. But here, because t is a little bit bigger than a half, this number is a little bit bigger than 1. So if you did that, the other half of the Lagrangian is going to get pushed off, and it's going to intersect this L12 here. So it's not going to work. All right. So I'm just saying, so something as naive as this would fail. All right. But exactly because I'm missing this line, there's another move. There's another kind of Hamiltonian I can define. So because you're missing this diagonal, you can make diagonal moves as well. All right. So you can define. Right. That's all you have to do here. Right. So you can define a Hamiltonian which depends on θ1 plus θ2 with positive derivative. Right. Or negative. Right. Positive derivative when θ1, θ2 is in t. Or in other words, θ1, I'm just saying as long as, so it's θ1 plus θ2 strictly less than 1. So if θ1 plus θ2 is strictly less than 1, I can make this derivative positive. Okay, so functions like that exist exactly because you're missing this anti-diagonal here. Okay, no, we're done. All right, so you look at a Hamiltonian like that. We'll call this H2 maybe. All right, and then so there has to be a step 0. That's the point of this. And then this just works out. Okay, so instead of doing that, so you make the step 1, you apply one of these functions, H2, to L12. Right, so what's going to happen? So the derivative of this is in the dθ1, dθ2 direction. So when you take the Hamiltonian, it's in the direction dr1 plus dr2. So when you apply that, this Hamiltonian is going to be moving, this Lagrangian is going to be moving parallel to that direction. Right? So the vector here, this is dr1 plus dr2. All right? And in particular, because the derivative is positive on t, the part of the Lagrangian that I care about is going to be pushed up some positive distance. So we do that first. That's kind of the step 1. So that just gives you a bit of leeway. And then, okay, so in principle, you'd have to work through the epsilons, but it's kind of clear it's going to work because you kind of have slack on how much you push this out this way. So if things were getting too close, you would just start with a polydisk where you have a bit more room this way. That's going to give you a bit more room close to the diagonal, and then you can push it a little bit further. So it's good. So there's some epsilons, but it's not like hard analysis or anything. Anyway, right, so you apply H2 to L12, and then step 2, you just go back to the first attempt, right? So then you apply the first H to L11. Okay, so you do this. So it's you do it as much as you can, but you still have the same problem. At some point, this is going to be intersecting L12 at the same time as it would before. But you can apply this for time, for almost all time. So exactly until this number gets close to 1. Well, I'm using t for 2 things at once here. Anyway, you can apply this Hamiltonian almost for all time until it gets up to this, right? Until the thing moves up distance 1. So which would be just short of time 1. Okay. Right. So you apply this to L11, and then you have to cut it off, right? So cut off near, well, right. So near the image under step 1 of the L12. Right. So it's right. So cut it off here. This is this right. This depends on theta, right? Yeah. Yeah. It's this exactly like this.
So is that t or is that θ2?
Good point. No. It's t.
It's a constant.
It's a constant. Right, because this is the derivative. Sorry. This is the derivative. Sorry. Right. Yeah, this is the derivative. Right. That's what I mean. Right. Right. Yeah. So what it's doing. So on t, the thing's moving down, and if the θ2 coordinate is bigger than t, then it's going up.
I missed something a while ago that's more basic.
Mm-hmm.
Your region, capital T, how do you get it in? Like, why isn't capital T forced to be the whole, square?
No. Because I'm just okay, you take the product of S and T.
Right.
They're still product sets, all right? So it's still going to be a product of some set in the R1 theta 1, some set in the R2 theta 2.
Right.
Right, but what they're looking like,
I see.
if you,
It
right, so
feels
it's like R,
It's not a fully toric.
no, okay, so it's like theta 1 goes, if you, like theta 1 goes a little bit less than a half,
Right.
and then R1 goes more or less out to 2, right? So it's some kind of, something like that.
Right. Yeah.
But it's still area 1, is the point.
Ah,
It's not, okay, that's the whole thing, right? It's not area 2, it's you're only doing area 1.
I see. I think I see.
Right, so just a product of two domains like this.
So it is somehow symplectomorphic to a polydisc or something.
Yeah, it's exactly right, yeah.
Even though that thing is kind of a weird shape.
Right, I mean, all you care about is the area of
Yeah,
this,
yeah.
right? Yeah.
Okay.
Right. Okay, well, so anyways, right, so I'm claiming, right, so you do this for time 1 minus delta just until it almost hits, and then for the last delta, you do exactly the same thing, right, but for time delta, but now you cut off, you don't cut off, right, so no cutoffs. Right. So this has exactly the same effect on L11. So we're still displacing L11 from the polydisk. As far as L12 goes, right, so L11, the bit in T is going down, the other bit is going up. The bit that's going down is going to be displaced. So L11, everything is fine. As far as L12 is concerned, it's only moving for time delta, which you can make arbitrarily small. So it's only moving for time delta, but I've already pushed kind of the problematical bit up a bit to get a bit of a head start. So as long as you push it up by 2 delta, when it goes down by delta for the last delta of a second, it's not going to run into it. So that's it. So okay. So anyway, so okay. So that's it. So in other words, well, okay, a bit short of time, but anyway. So this. So that's it. So somehow these packings aren't maximal. And that's kind of the thing. So it's well. So anyway. So just okay. So why? It's like 1 minute. Why? This is sort of applications of this. Does this make sense?
When you said
Oh.
these packings aren't maximal, you mean just the natural packings?
Right. The natural packings aren't okay.
You don't know if this is it.
Yeah, exactly. Right. So yeah, so that would be an open question, right? You could say somehow what is the maximal packing number of well, polydiscs? Right, 2 plus epsilon, 2 plus epsilon. I don't know, right? But I know the answer is at least 5. All right, because I mean, so the maximum packings are how many Lagrangians can I get in there, which is disjoint. I've shown you 5, but it's possible you could do something completely different and get infinity in there, right? So there's no obstructions to that. So it's,
No. Right. You don't know of any obstructions.
I don't know of any obstructions, right? Yeah. Or maybe there's just a construction and you can do something clever.
What do you think?
No idea. Well, well, okay, that's okay. There's some kind of okay. Right, so okay, so I was trying to work this out then. So now, what I was going to say here. Right, so right, so okay, so applications of this. So there's a paper of right, I'm out of time, so it's anyway. Right, there's a paper of
We started a little.
I started late, exactly, right, okay. Right, so I got this, right, okay, exactly. I started a minute late, so it's okay. Right, there's a paper of Lazzarini, right. I got this from Felix Schlenk, anyway. There's a paper of Lazzarini, Marco, and Sauvan, who work in dynamical systems. And they said, okay, let's take an integrable system, then you understand the dynamics pretty well, right? In other words, the flows preserve the invariant tori. But then you perturb an integrable system, and then they showed there exist wandering sets. So sets that kind of, if you take, say, the time one flow of the Hamiltonian, and the set never comes back to itself. All right? So perturbations of integrable systems get extremely difficult. Right? And perturbations of integrable systems look kind of like, so there's still going to be some invariant tori left over. All right? Okay, so then they were saying, okay, if I perturb an integrable system, then I can get these wandering sets. So that's sets where you keep applying the Hamiltonian and you never intersect yourself. And then, okay, and then they were saying, well, how big can these wandering sets get? And then kind of a test case is, try and work out the Gromov width of maybe R4. So let's just suppose the invariant tori that survive are exactly the integral ones. All right, so the union KL, suppose natural numbers. Okay. All right, okay. So anyway, that's an open question. And again, that could be infinite. But the point is, the only so now you can do exactly the same kind of trick, right? So now, so okay.
Why does that answer it?
It doesn't answer. Oh, this question paper. I'm not saying I can answer it.
But why would that tell you how big a non?
Well, it would be an upper bound for the size of a wandering set. I mean, assuming you perturbed your integrable system and this was exactly the tori that were left, then you could say, well, okay. So, well, and then you say, okay, so how are you going to measure the size of a wandering set? Maybe you're going to measure it by the Gromov width or something. So this would be an upper bound on the, yeah. Right, okay, the only obvious ball in here, so Gromov width you're interested, the only obvious ball has size 2, if it's an open ball. Okay, and then you can, right, but then, okay, so it's not hard, you can do a little bit of holomorphic curves. If you take a ball of size 3, well, there's only one in here, L11, the Gromov width of this thing is 2. Right, so it's somehow, right, so if you cut it off there, you can't get a ball of size bigger than 2 in that. Basically because this cobordism that's left over is foliated by holomorphic curves of area 1. So that's okay, so that is 2. But suppose now you allow yourself a little bit more space, and okay, so unfortunately you have to go out to 4, which is this line here, I think. All right, so this would be 2, 2, 3, 1. All right, so now, okay, so if we ask the same question, I have to go 4 plus, right? So 4 plus epsilon. Right, but now there's a whole bunch, right? So there's all 4 of them. Right, just script L. So that's all 4 Lagrangians sitting inside there. This is bigger than 2 now. All right? And exactly the reason is exactly the same thing. So you could just copy this proof, but take S to be almost the whole thing. So that goes out pretty much 4 on both sides. So then when you take the t factor, it has to be close to a half. And it again lets you make sort of diagonal moves. So it's the same kind of thing. So once you go out to 4, you can kind of you can somehow prove right. There's right. You can get bigger balls than you would expect by the same kind of construction.
How big? I mean, you say greater than 2.
Well, okay. I don't know how to. Okay. Well, there's a case. Okay. Which, okay. I don't know how to get optimal estimates. So I can get like 2 points, less than 2.5 somehow. Oh, and it depends how fast you go out. So it goes out like a factor of epsilon. So I can get up to 2 points. You can do like 2 points something. And it's not a huge number because I don't know. Once it gets to 5, there's a whole bunch more Lagrangians, which is too much to worry. I can't deal with them. Too much to worry about. But as long as you're up to 5, you can sort of grow this thing and get more in there. Yeah. Okay. Right. So it's and then anyway. Well, right. Yeah, I don't. Right. Well, so the only way I know to get optimal cases is to kind of manufacture. All right. So you can sort of embed. So you can look at embeddings of, let's say, like DC. All right. Okay, that's right. Let's say 0, 1. So this is supposed to be the R2, theta 2, and then I want to get this inside. So a cylinder, right? So I'm interested in cylinders, but with bounded derivatives to get the proofs to work, right? So something like in the polar coordinates, right? So some kind of derivative bound. All right, so what we're looking at here. Right, so the range goes up by R, goes along, and then there's a bunch of, so you have to embed a cylinder missing these Lagrangians. Right? So the way this goes, if R is less than 2, then it's if and only if C is less than 1. All right? Oh, okay. Let's say if R equals 2. All right. But if R equals 4, then again, it needs to be right. Right. So once R gets to be 4 plus, I guess. All right. So once R gets to be 4, then you can get a bigger thing. Right. So this is if and only if C is less than 2. Actually, 4 on the dot. Right. Okay, so somehow, and it's exactly the same reason. So once you get to 4, you can kind of spread out in the S direction, and you've got enough room to make the diagonal moves. All right? Whereas in this case, when R is 2, you haven't. All right? So when R is 2, there's only one. Right? There's only one family of Lagrangian tori in there. These things bound Maslov 2 disks, and they kind of obstruct things. So anyway, well, okay. So anyway, so all this. Right. So there's definitely okay. So I suppose my point. So these things have more area, more size than you would expect, but it's not necessarily so easy to estimate exactly. I don't know exact bounds on it, like exactly what these Gromov widths are. I suppose that's the. So anyway, sorry, but I'll leave it there. Yeah. Thank you.